Yeah, so hi, I'm George. I'm the founder of Stakpak, but I'll tell you about that at the moment. But this is about making coding assistants smarter for DSLs, not DSLs specifically, but like for things that require like the worst part of coding that LLMs are terrible at. So to tell you about that, whoa. Okay, tell you a bit about me first. So I'm the founder of Stakpak. Stakpak makes the worst part of coding that LLMs suck at, which is infrastructure and DevOps work, configuring all the different DevOps tools together, much easier, so developers can have more fun building products. Before that, I was a founding engineer at a couple of startups. I love doing calisthenics, which is like bodyweight exercises, riding motorcycles, and volunteering tech community, running free boot camps and stuff like that. I'm really into developer experience and security, which are two things that usually don't mix really well. Yeah, and today I'm going to talk about DSLs, not specifically DSLs, because if you have a YAML file or JSON that follows a specific schema, it's not a DSL, it's a generic like configuration language, but LLMs still suck at it. They're pretty terrible. And to give you an idea of what DSLs are and why they're important, we use them in every single project, like SQL is a DSL, Terraform code, Docker Compose, GraphQL, Kubernetes manifests, Rego. Anyone written Rego before or OPA? Yeah, most people don't. So yeah, so we use all these kind of different DSLs in our projects in different ways, and LLMs are pretty terrible at them for the following reasons. We're going to explain why, but we need them in our coding. And LLMs are really good at the good part of coding, which is writing the actual code, but they're pretty terrible at the part we don't enjoy, which is figuring out all these different DSLs or domain-specific languages. So why LLMs suck at DSLs? So this is a paper about domain-specific languages with two different evaluation methods I will describe now, trying to explain why LLMs suck at DSLs. So you would see on the left column, there's a stack eval. So these are a set of questions from Stack Overflow about different DSLs and answers. And here they're evaluating different models on these DSLs. And on the other side, you'd see Stack Unseen, which are very recent, more fresh Stack Overflow questions that most likely the model was not trained on. And you'd see like the performance falls rapidly with the unseen data. So one of the main issues with DSLs is they keep changing quickly. And not all of the DSLs have a lot of data compared to JavaScript and Python, as you can see on the graph on the right side. So the performance drops greatly the less popular the language is, and the less data that went into training the LLM. So there are two things here at play. So how much data was in the training data set of the LLM from these DSLs, different DSLs or less popular languages, and at the same time, how fresh this data was. Because when you see the freshness of the data set or the questions drops for the most recent questions, performance drops as well for domain-specific languages. And the less popular the languages, performance also drops as well. So the main issue with DSLs, they're very fragmented. There are a lot of them. So there are not a lot of data in the data set about these DSLs. And the more the DSL or the schema changes frequently, the worse the LLM would do. So to give you an idea of this, for example, if you compare JavaScript to Kubernetes manifests, as if you consider this like specific schema of configuring Kubernetes DSL, Kubernetes gets a new major release, a new minor release every 3 months. So it keeps changing. So most LLMs don't know what the latest version is. So definitely to perform worse, according to this study. And Kubernetes is just very recent compared to Python, for example. Like how often does the Python syntax change compared to Kubernetes manifest schema or like configuration parameters? So yeah, that's basically why LLMs suck at DSLs so much. This is something we ran internally, trying to compare different open source and closed source LLM models. I'm not sure, like the text is pretty small, but like here you'd find MetaLlama, Mistral, GPT-4o, and Claude 3.5 Sonnet on different applications. So we were generating Terraform code for different cloud providers. And we found out that there's another factor. So the freshness is a factor, the popularity of the language is a factor. And the third one is the task itself. So you would see Llama sucks pretty much configuring Azure. It's pretty terrible at it compared to other models. And they perform differently for different cloud providers. So the task also impacts how these LLMs perform on different DSLs. So today I'm going to talk to you about 4 techniques. some of the stuff we tried. These ones fit together, like you can see they're burger. So it would help you remember them. But there are other things we keep trying all the time to make LLMs better at these kind of DSLs and like configuration languages. But the four we're going to talk about are bounded decoding, retrieval augmented generation, grammar prompting, and recovery. There are more obvious things related to prompting techniques, but these are the ones that like had the biggest impact. So the first one is bounded decoding. So first, let me know, like, who's building an LLM-powered app here? Who's building LLM agents? Okay, cool. So bounded decoding or structured generation, this is how to do proper structured generation. So to give you an idea of how it works, we'll take an example. So this regex, can someone tell me what this regex does? In the middle, the one in the middle. So this is a regex for creating a number with a decimal point. So the first part is you have one or more digits, and then an optional decimal point, and then 0 or more digits afterwards. Okay? Yeah. Yeah, I didn't escape the dot. So this hopefully generates, and actually, like, there's also another mistake, like the D behind, like the digit behind the dot. Like, if you have a dot, you should have a digit. Like, you shouldn't have a dangling dot. So assuming this is a valid regex to generate numbers with decimal points, so how do we force the LLM to generate valid numbers every single point of time, like 100% of the time? So this is what bounded decoding does. So how LLMs work, like I'm butchering this, but like the last layer, you get like the probability of different tokens. So if you have these input sequence, 7, 4, 8, you get from the LLM the probabilities of the next tokens. So for the plus, you get 3% probability. Foo, you get 4%, assume this is a token. And then dot, 7%, and so on. So what structured decoding is, we take a regex, and then we build a finite automaton based on this regex. So we start, and then we have a digit between 0 and 9. And then we have another digit, because this is at least one digit. And then we can keep going, generating more and more digits. And at some point, we can end. It's an integer. There's no decimal point. Or we can add a point, and then add more digits, as many as we want, and then end. So do you understand this automaton? How it works? Yeah, it's pretty simple, right? OK, so we use this and walk step by step, taking in the input, and we zero out, we mask the probabilities of all the tokens that are not valid as transitions. So in this case, we're in this state, and the valid tokens are either another digit or a decimal point. So anything else we just mask out. We zero the probability. And then we continue decoding as well. So we can only get the next token, and we would still be valid within this automaton. So the cool thing about finite automaton is you can turn regexes into finite automatons. You can turn a context-free grammar into finite automaton. So generic programming languages, they're not all context-free, but you can define, in most of the cases, a simpler version of the grammar, which is context-free, which then you can turn into a finite automaton, and then you can control decoding this way. So the cool thing about this is you can take, for example, like what we did. Like we created a context-free grammar for Terraform, and then we created a finite automaton based on that. And then we get 100% of the time valid Terraform every single time. So we forced the LLM to generate valid DSL every single point of time. This is how to do proper structure generation. So some LLM providers like Anthropic, they don't do that. Like they rely on the model being very smart. So they try prompt it into generic JSON, but it screws up for tool calling, for example. But GPT-4 and using this library, like this explanation, I brought it in from the .text outlines documentation. It's the best one out there I found. And if you use the outlines library on top of an existing open source LLM, you'll be able to do that, like generate 100% valid output every single time. So this is how it shows. So I use this test a lot to make sure structure generation is proper. So when you use this technique to make sure you generate valid Terraform code and you ask the LLM who you are, so the LLM will output something like this. So this is basically, for those who don't know Terraform, null resource that uses a local exec provider to echo out, I am a DevOps engineer. So it forces the LLM to generate valid Terraform code, even if you ask it something outside like of the bound tasks or like out of domain. And LLMs are pretty clever in finding workarounds. That's why this works. So the second technique in Burger is retrieval augmented generation. Who's familiar with retrieval augmented generation? Okay, so for those of you that don't know retrieval augmented generation, you basically take in the user prompt and context, like selected bit of code, or the user's environment, like Cursor takes in the project's code or like external documentation, whatever, and then you retrieve more context. And this context can be anything, like it can be related code, like the first version of GitHub Copilot, and it can be standard operating procedures, your own set of best practices on how you want to generate stuff. It can also scour the web, like scrap web pages, and it can be documentation, it can be anything. And then you use the user's context and this external context to generate something. And this usually improves performance or makes the LLMs more customizable. So this is the generic idea. So what we learned was that there are 3 things, at least you can do, to make RAG much better at DSLs and like very specific configurations. The first one is query expansion. So you don't just like take the user query and then try to retrieve whatever context. You can use an LLM, which can be a small LLM, it doesn't have to be smart, to break down the query and rewrite parts of it. So one thing you can do is extract keywords, which we found is amazing for DSLs, because in DSLs you have a lot of very specific technical keywords and abbreviations. And these abbreviations make sense within the DSL, but they don't make sense to the LLM because this is a very minor part of the data set the LLM was trained on. The other part we found that works really well is rewriting the user query into a more expansive query that may helps the LLM understand what the user is asking for, and filters. And this works really well compared to semantic search because most people doing RAG with semantic search, when it comes to domain-specific languages and domain-specific problems, it's super tough because people create the DSLs to be more succinct, to be able to express stuff to configure complicated tools in a very easy, succinct way, instead of having to explain and elaborate. But the LLMs don't know that. So you need to expand and elaborate to make it easier to match with relevant outside context. So I found keyword matching better than semantic search when it comes to retrieval with DSLs. The second part is documentation. So why GitHub Copilot and Cursor suck so much at this kind of infrastructure work is that they reference mostly code samples, not documentation sources. So we found if we replace RAG using code samples with documentation sources, you get better, fresher results. Because, for example, for Terraform, like how many companies open source their Terraform code on the public internet? Most people don't. So most of the Terraform code out there and the Docker files are outdated. They're pretty old. So when you reference the latest documentation, you get higher quality results, although the example is no code, it's just docs. The third thing we found out that make RAG much better, and this is a recurring theme, we mix static analysis with generation. So in this case, we use TreeSitter, which is like a generic parsing, like generic parser. It parses most of the popular languages. And we parse Terraform code, Kubernetes manifests, Docker files into code blocks. And then we figure out the relationships between these code blocks. And then we generate summaries to index them. So instead of retrieving bits of text or blocks of text from your configurations, we actually understand the structure of the configurations and the relationships. And we use this to build more intelligent RAG. And we use this to be able to retrieve parts of your code. And since we know the relationships, it's not just semantic relationship. It's actually the very deterministic graph of the components building your infrastructure or the relationships between the steps of your CI/CD, for example, and so on. The third technique of Burger is grammar prompting. So you can find the paper down there. The grammar prompting paper basically does is it defines the grammar of the DSL or the language you're trying to generate in BNF format, and then adds a couple of examples, like a few-shot prompting, and then prompts the LLM. So it basically tries to teach the LLM the rules of constructing stuff or generating stuff in this language, so it generates more accurate results. So we tested this on internal DSL generation benchmarks and increased performance by 12%, which is amazing. But we found this actually much more useful for DSLs that are brand new or not known. For example, we were building an endpoint to transpile your Terraform code into an architecture diagram using a diagram with code tool called Razor DSL. And Razor, are you familiar with the Razor, the diagramming tool? Okay, so we invented a new DSL to draw architecture diagrams. So no LLM know about this tool. So what we did is we created a simple grammar for this tool, plus their documentation, and we grammar prompted it, and it just learned how to generate code for this DSL. So this works great, but the other techniques are better at well-known DSLs. This is perfect for newer DSLs that the LLM knows nothing about. So using this technique with a very old, very small model, we're able to generate architecture diagrams using the DSL, Razor DSL, with like 8 times less the cost, 8 times faster. And as you can see, like you can even see the the cost reduction. So compared to O1, with this basic technique, you're able to generate stuff 8 times faster and at least 500 times cheaper than O1 with just a simple model. And it's the same for all these techniques. So we were able to beat Claude at DSL generation with a Llama 3.1 model, which is super old and super small. So we don't need smarter models. We just need more reliable systems built around these models. So the final one, which is pretty obvious, recovery and retry. So what you do here, you also need static analysis, because when you generate code with the DSL, you need to make sure the DSL is working. So you try to parse it. If it doesn't work, then you take the feedback from the parser and then give it back to the LLM to try again. It's simple, but it works. And if you parse it and it works fine, it doesn't mean it's done. Like, you need to validate it. If it's a Terraform resource, for example, you need to validate the schema to make sure all the attributes are there. There's nothing deprecated. It actually should work with the latest schema. Because, like, for example, for Terraform AWS, you get a new provider version every 3 or 4 days. So it keeps changing really fast. And if you validate it, you get some validation output that's not valid. You give it back to the LLM to fix it. So it's pretty simple. This has got even more interesting with agents. So we've been building agents architecture to try and make this even better, because we figured out even if you create valid configurations and you push it to production, it would just fail. So we name our agents after minions. And we found out like the most interesting architecture is Norbert, which is the naked minion. Do you know Norbert? Okay, so why the naked minion? Because this is a very stupid and simple agent architecture. It can do only 2 things. It can ask the user for input, and it can run a command on your machine. And even with this very simple agent architecture, it was able to fix issues that we couldn't detect deterministically using validation and parsing. For example, you can reach the limit of the VPC, number of VPCs you can create on AWS. You can forget to install some stuff or like configure credentials in your machine. And with this more smarter kind of retry and recovery mechanisms, you're able to fix more issues. Yeah, and that's basically it. I would have loved to talk more about evaluation, but that's also a bit like a big topic on its own. So please reach out. And yeah, thank you. Any questions? Yeah.
So this is I'm assuming off of human generated DSL. Tried value LLM generated DSLs. If you tell the LLM generated DSL, do you find that what it produces might be immune from some of the?
No, I haven't tried LLM. I'm sure LLM can generate DSLs, but I haven't tried. But like, even if the LLM generate DSLs and then you're trying to make another LLM work with these DSLs, you would have to use some of these techniques to make it like be able to figure this out, because it's not inherently like built inside its memory or like parameters.
Would humans be able, would developers be able to LLM generate DSLs?
Yeah, we'd have to learn it. This is exactly the same way. Like, all these techniques we're trying to teach LLMs how to understand the DSL and do better. So yeah. Yeah.
Yeah. So when I was first looking into that, when I added some Llama CPP, looked like the grammar language that you find was very limited. It didn't have like the richness of the. It sounds like your technique was to make the superset.
It's a more generic grammar. It's manual. Like, we tried using, for all of these things, we use LLMs to refine the prompts and optimize these things. But like in writing grammar, it's pretty terrible. So grammar itself is in a DSL. And this is one of the very few cases when if we would try these techniques to make it better at writing grammar DSLs, it's not even better, because it's a lot like it's more complicated. It requires a lot of reasoning and to be able to structure the grammar. So this is basically a very slow manual process of iterating on the grammar to make it generic enough. So Llama CPP, for example, would be able to understand it and generate. At the same time, it wouldn't time out, because it can take you a lot. Like, if you have a lot of branching within the grammar, for example, it can time out and just like generate nothing. So it's not the full grammar for the thing you're trying to generate. It's more of a bounded approach. And we found that LLMs are very sensitive to the grammar. So if you switch around some rules, it would be like prompt engineering. So you have to mix the grammar with prompting. and the LLM is sensitive to the grammar. So the way you structure your grammar would generate different results. So the combination of rules and how you break it, it also matters. For some reason, I'm not sure why, but it does. Any more questions? Yeah. Yeah. Tried what? Have I tried what? We'd actually no, but we're trying that for agents. So one of the things in evaluation is that you need some sort of high, like there are three levels of evaluation for agents. At least that's what we discovered. You can evaluate the end goal, you can evaluate sub goals, and you can evaluate the trajectory of thinking, like having a partially ordered plan of some sort. And to have this partially ordered plan, you need a lot of examples on how to accomplish the tasks, like how the sequence of steps to achieve the task. And we couldn't find a data set for DevOps tasks. So what we're doing is we're creating very stupid agents like Norbert that keeps basically like a Terminator that tries to accomplish the task and fails most of the time. And then let it run on different scenarios and then filter these scenarios with the ones that succeeded. And then take these, generate standard operating procedures or like a word model to guide the agent, and then try again and keep doing that until we have like a nice data set. That's as close as we got to reinforcement learning. Okay, thank you.